thank you for giving me the opportunity to talk to you about my research and report on what has been done ever since we first talked. So today's topic is going to be our planet, the Earth, but we won't focus necessarily on what's at the surface, because what I'm interested in typically is the structure of the Earth deep down, what's below our feet and what we cannot really see. So for the premise of this talk, I'd like to say that although the radius of the Earth is 6,400 kilometers, the deepest drill that was able to be achieved by humans was around 10 kilometers, which is not even scratching the surface of our planet. So 10 kilometers is still in the first part that we call the crust. We can get back to it later, and we don't even sample the mantle. So in order to infer what is below our feet, we need to find other ways to probe it. And the same way that when you go to a doctor and he performs a CT scan on you, he doesn't need to drill in your brain to actually visualize what is there. We can do the same with the Earth and use some techniques that use wave propagations in order to understand the composition and the structure of our planet deep down. This way we can see some mechanisms that are happening in the mantle, for example, which is the object of our interest in this study. Outer core and inner core are also very important for the dynamics of the planet, but they use either other tools or they use other methodologies that I'm not going to get into. But first, let's get back to the surface for a second. And one of the main discoveries of the late 60s was the existence of those plates that are at the surface of our planet and that are moving relative towards each other, and that basically segment our planet into roughly 12 plates that, as I said, move around each other. However, they are very important for the dynamics of the planet because they are the surface expression of what is going on throughout the mantle and throughout the whole machinery that is our planet. And also importantly, we have most of the earthquakes that are happening at the boundaries of those plates. So as I said, those plates are just the surface expression of something that is much more general, much more 3D, if I may say so, which is a circulation that takes place throughout the whole mantle, and that is the consequence of the Earth evacuating its heat that it gathered at its formation. So whenever the Earth was formed, it accumulated a certain amount of energy that it is now trying to cool down in order to basically achieve equilibrium. And one way to cool down is actually a mechanism that is called convection. And you're seeing now convection cells, which basically take the heat from the core mantle boundary and then slowly takes it back up and then evacuates it at the surface. And when I said that the plate tectonics were actually the surface expression of those convection cells, well, you might see that here you have a cartoon example of what is a plate, and it is actually moving because of this, like it's just the upper part of this convection cell. So one of the main tools to actually achieve to image what is happening deep down is something called seismic tomography, where we use the propagation of the seismic waves in the Earth. And because when the waves are triggered during an earthquake, they propagate, and they propagate in all possible directions, and they interact with the medium. And when they interact with the medium, if you record them at enough stations, we will be able to see how they have interacted with the medium in which they propagated, and infer some properties of well, this medium in which they propagated. And when you have enough sources and enough stations that will be located throughout the surface of the Earth, we are able to reconstruct 3D models of what the velocity of the waves look like, and the velocity of the waves are a proxy for the temperature, like a mixed effect of the temperature and the composition of our planet and the mantle. So here we have an image of this of the Earth at 70 kilometers, and red includes red means that it's lower velocities, and when it's more blue, it means that it's faster velocity. So it means that when waves travel around this area, for example, they will be slowed down, whereas when they travel throughout, let's say this area, the North American Craton, they will be their travel time will be shorter. And what does it mean to have slower velocity? Well, in this case, the slower velocity means that the temperature is higher, because when you propagate a wave in a higher temperature material, the velocity at which it propagates will be lower. Whereas when you propagate waves in a cooler material, then it will be the velocity will be faster. So what we see in this image is actually that the red part, the slower part, the higher temperature parts correspond exactly to the different plates. And here, for example, you have the ring of fire that we can observe. So 70 kilometers is what we call it is still what we call in the lithosphere, but that's just another example at how the plate tectonics actually work, and how we can observe it also not only at the surface, but using the seismic tomography. But we don't have to look at only 70 kilometers. We can look all the way down to the core mantle boundary, 2,800 kilometers down, roughly. And when you do this, you observe some structures that are deeply rooted in the core mantle boundary, for example, here, and that have an expression all the way to the surface. That is what we call mantle plumes or hotspots. And if you remember the cartoon of the convection cells, well, this is the upwelling part of the convection cells. So we are able also to image this with this methodology. And although there are places where we're not sure where the plume is rooted, there are places where it's very clear that it's rooted at the core mantle boundary. For example, Hawaii. So what is the problem with seismic tomography? You might say, well, we kind of figured it out. We have everything we need. We don't really need to explore much more. However, as I said, the velocity is sensitive both to the temperature and the composition. And it's difficult to kind of pinpoint which part is temperature and which part is composition, especially in the lower mantle at the core mantle boundary. And one of the very important questions for the dynamic of the planet is whether or not the layer that you see here, for example, does it mean that it's is it lighter material, lighter than average, or is it denser than average? And that has important consequences for the geodynamics. And unfortunately, the seismic waves, that we're using are not very sensitive to the density. So we have to find kind of other types of data sets that would be maybe more sensitive to the density structure. And this is what some people had proposed, is that to use the rotational dynamics in order to infer the density, because the rotation is directly sensitive to the density and not sensitive to any other elastic constants. So if I backtrack a little bit, we all know that the length of day is about 24 hours. That's we've known for many years, if not millennia. What is less known is that around this 24 hours, there are some oscillations that are on the order of magnitude of the millisecond, for example. And when you look more closely at the length of day data in the time series, you see that there are multiple periods that can be observed. And there is one that is particularly interesting in the observations, and it's one that has a period of around 6 years. And it's long-term oscillations, and you can find them pretty consistently because we have now very long time series for the length of day because of the GPS stations. And because of this period, you need a physical process that basically works at the same period as the 6 years. So you need some, in order to have a length of day oscillation of 6 years, you need a physical process that also moves around 6 years. So one possible explanation, one that we have been focused on in our work, was that it was basically an interaction of the gravitational structure of the lower mantle with the inner core, where the lower mantle was actually exerting a restoring force on the inner core, which was making the inner core oscillate around maybe that could oscillate around 6 years, and therefore you would see a 6-year oscillation in the length of day. However, in this paper, they made computations for what the period would be, and they were getting results for like 2 or 3 year period. However, in this study, they were not really taking into account the most modern approaches for the structure of the Earth, and also there was no systematic studies of what was the sensitivity, what was this oscillation sensitive to in the lower mantle. So this is what we've been working on. We've tried to basically get to see if we could reconcile the observations with the theoretical computations. So just to come back again on the mechanism, this is what I was explaining a bit earlier, is that we call those LLSVP for large low shear velocity provinces. It's features that are pretty consistent across all the tomographic models. You have 2 LLSVPs, one under the Pacific and one under the African continent. And basically the exchange of angular momentum between the denser LLSVP and the inner core would generate this restoring force on the core that would then oscillate at a certain frequency, and this frequency might be seen in the length of the oscillation. So this is the case if the LSVPs have are denser than average. And if it's the case, then they exert a force on the surface of the core mantle boundary and deform it such that you have topography at the core mantle boundary, and having a topography at the core mantle boundary is something that has been observed and something that we've known. So this is the case for denser LSVPs, where isostatically you have to have a core mantle boundary that is deflected towards the center of the Earth to accommodate for the weight. And on the other case, where you have light LSVPs, then you have a deformed core mantle boundary, but deformed towards the surface because of the lighter LSVPs than average. So we perform sensitivity analysis because we want to know whether or not this oscillation is sensitive to the core mantle boundary or not. And what we found is that indeed, so here we have the sensitivity. So if you change the density at around this depth, then this is what will show the most differences in the periods. So let's say here you don't have a lot of sensitivity. If you change the density around 1,300 kilometers, it won't change much the period. However, if you change the density around the core mantle boundary, this will have a great effect on the period. And it has little sensitivity at the surface, as you can see here, and it has maximum sensitivity around the core mantle boundary, which is very good for our case because this is exactly what we want. We want to focus on what is the structure at the deep mantle. So we want something that is very sensitive to the deep mantle. And another advantage of this is that it's only sensitive to the density structure. So we won't be very sensitive to the temperature, really, or we won't be really sensitive to what can affect the seismic waves, and that leads to this, it's not a paradox, but leads to this, it's not really a discrepancy, but it leads to the fact that we cannot discriminate between the temperature and the compositional aspects of it. So now we are ready to tackle basically the next part, which is we want to test different models for fixed layers of fixed thickness of LSVPs. We want to compute what are the theoretical periods associated with it. So in this figure, I show the period as a function of the density perturbation and the topography at the core mantle boundary. And in white, this is the part of the parameter space that corresponds to a 6-year period. And in the dashed black lines here, this is like 5 years and 7 years. So it's kind of the acceptable range of what we can find, of what fits the data, let's say. So one very important thing that I want to say here is that we're not trying to construct models for LSVPs because we only have one data point. And it's not very reasonable to go around and say that, oh, we'll just constrain the LSVPs based on this data point. But what we can do is test the existing models for LSVPs and test whether or not they fit this independent data set, because no model for LSVPs we're actually constructing using this in mind. So we have this independent data point that basically can give you an idea whether or not it fits the rotational dynamics. And this 6-year oscillation restricts the simple parameter space, as I said, and it constrains topography and density perturbation for fixed thickness of LSVP. But this is when I consider only negative density perturbation and negative topography, but we can expand this in all possible directions, and then we get this figure, which is basically the same. It's just like we consider all the different quadrants for the density perturbation and the topography. So once again, you have the white line, which is 6 years, and that corresponds to a 6-year oscillation, and the black lines are 5 and 7 years. And one thing I added to this figure is that, I'm sorry. One thing I added to this figure is the isostatic topography, which is if it was compensated for just if the LSVP structure was compensated isostatically by the topography, this is what the period would look like. And even in the most favorable cases, which is like positive density perturbation and negative topography, so it's the left case on the figure I showed earlier, and negative density perturbation and positive topography at the CMB, which is the right figure on the mechanism figure. We can see that even the isostatic topography doesn't get us close to a 6-year period. So what that means is that even in the most favorable cases, you still need something that's called dynamic topography in order to reach the 6-year oscillation. And moving forward, I hope I convinced you that the rotational dynamics and the length of day oscillations are interesting independent data sets that it is worth look into in order to constrain some of the mental dynamics. And because we have now enhanced instruments and longer time series, we can get to those oscillations and maybe discover more of those oscillations that can correspond to other processes. But there's still a lot of efforts to understand precisely this, where the signal we see comes from, because there can be also other explanations for this, and we need to really push into this direction to make sure that it is this mechanism that causes it and not another one, or try to find a way to reconcile all the possible mechanisms that exist for this length of day oscillations. Thank you very much.
Quick question. Can you explain a little bit more about the length of day oscillation? You said in milliseconds or something?
Yes. So, okay, if I take an analogy, like the usual analogy that is taken for length of day oscillations are a rotating ice skater. So if you're ice skating, and let's say that you're very good at it and you manage to rotate, and you carry something that is called angular momentum, and because you have to conserve your angular momentum, if you close your arms, you have to basically rotate faster in order to conserve your angular momentum. Well, this transfer or angular momentum does exactly the same. It just it plays on the rotation rate of the planet, and this is why it makes it oscillate around the 24 hours that we know, but it makes it oscillate by different milliseconds. There are other ways that you can modify the length of day. You can modify the length of day, for example, when you have an earthquake, you redistribute the masses. So for example, when you have a massive earthquake, let's say magnitude 9, you will see this in the length of day. You will see that in this day, there will be like milliseconds, like the day was shorter by milliseconds or longer. It kind of depends. Or if you have a meteorite that impacts the Earth, you will also modify the length of day.
Oh, so I understand that if you measure accurately the length of day, actually changes, oscillates in milliseconds.
Yes. Yeah, and this is one, like this 6-year oscillation is one of the periods that we see in this length of day data. There are also a lot of other signals that we see, mainly atmospheric signals, because the atmosphere is a mass that moves around, and it also participates in this angular momentum exchange and changes the length of day.
Mm.
But this 6-year doesn't really fall into this atmospheric forcing, because exactly it is too long of a period to be considered to be to be actually led by the atmosphere, because
yeah.
the time scales in the atmosphere are much shorter.
Yes, so that effect, the atmosphere effect, cannot be causing this type of long time frame. So what you're saying is the 6 years is a data point that doesn't change. So you're trying to fit this to your simulation of what internally the mantle and the core interaction.
Yes, so we have we can compute what theoretically the period would be for a given distribution of density in the mantle. And this is what we're trying to get closer to 6 years rather than the 2-3 years that we see here. So this is why we introduced topography, and this is why we introduced a lot of different things.
And the ultimate goal is to really get a much clearer understanding of the composition of the mantle.
It's to answer the question whether or not the large low shear velocity provinces are lighter or denser than average. But as I said, this one data point is not really going to give us the answer. It's like everything in science. It's not like this one thing that will give us the answer. It just participates into, saying whether or not the existing models fit this data or not. And if it doesn't, then maybe it means that the LLSVP model is not accurate enough, or it's not good enough. But before we can say things like this, we have to make sure that what causes this 6-year oscillation is the exchange of angular momentum between the lower mantle and the core.
That's understanding, a clear understanding of the composition of the mantle and its the convection flow and such will help scientists to predict the potential earthquake.
So predicting earthquakes is a very tricky topic, in a sense that we're now, there's a general consensus in the community that it is not possible to predict earthquakes, because predicting earthquakes mean a few things. But in order to say that you predict an earthquake, you have to give a location, you have to give a magnitude, and you have to give a time when it happens. I can say there will be an earthquake tomorrow, and I'm 100% sure to be right, because there are earthquakes every day. What I cannot say is that there will be a 7.5 earthquake in San Francisco in 2 years, for example. And this is because the mechanism that we are talking about, like the rupture, what onsets an earthquake, is extremely complicated, and you can never really say if the rupture is going to stop at the scale of a few atoms, in which case it's not going to be anything that is remotely something that you can feel, or if it's going to be across hundreds of kilometers and generate devastating consequences. So predicting earthquakes, there's a consensus that it's not really possible, and no one really is pushing in this direction. There are other things. So forecasting is a very different thing. So for example, if I say there's like 70% chance, 70% probability that in the next 30 years, there will be a magnitude 6.7 or above in the Bay Area. This is forecasting that is based on a lot of different things, a lot of different observations. And that is something that people work on, and they establish maps of risks. And that's something that, it's an active area of research. It's very different, like forecasting and predicting are two different things. And unfortunately, knowing more about the large scale mechanisms of the convection, for example, is not going to give us much more than this, because it happens at a scale that is not very relevant for the onset of earthquakes.
I see. Okay.
Actually, a little while ago, I heard that actually California with they would be able to predict a few seconds before an earthquake actually happens. So
Yeah, so
I,
it was, yeah, sorry, it's called early warning, and it's actually it's like main developers of Shake Alert, which is for California, is actually here at Berkeley, and in the Berkeley Seismolab. So it is not really predicting, in a sense that it relies on detecting the earthquake as fast as possible, and measuring what we call the P waves, which are the waves that travel the fastest. So you catch it as fast as possible, and then you predict when the most devastating waves will be arriving. So the most devastating waves are typically surface waves, and they travel much slower. So it relies on two things. It relies on the fact that the devastating waves travel much slower than the primary waves. And it relies on the fact that we can send electromagnetic signals much faster than the waves travel. So, for example, the BART system in the Bay Area is equipped such that if there is an alert, it automatically shuts down. And that's it gives, for example, so the alert time that it gives you, it depends on how far the earthquake is, but typically it's in the order of magnitude of seconds. And those few seconds, you can actually do a lot of things. You can shut down BARTs such that when the waves arrive, if the train derails, it doesn't derail at high speed. You can also shut down some power plants, can do a lot of those things, and you can alert, you can push notifications on everyone's phones to tell, well, now it's time to take cover. So you have to do three things. You have to drop, cover, and hold on. So it gives you exactly this time to protect yourself and lower the chances of being harmed by falling objects or other hazards like this. But it doesn't fall in the scope of predicting, because the earthquake has already happened. It's all a matter of like catching it very early on, so that then you can send an alert to a broad area.
so you say any way to improve on the measurement so that, you know, we can have, instead of seconds, have minutes of warning?
No, because the seconds, it's not because we don't catch it fast enough. I mean, you can always improve how fast you catch it by putting more stations and trying to like do more progress on the algorithm side. But you'll always be limited by the fact that the waves still propagate at the speed at the velocity that is around a few kilometers per second. So it will still travel fast, and the seconds really is because, well, I mean, if it's like, in order to get to minutes, it would be that you're so far from the epicenter that the P waves and the surface waves are actually separated by minutes. And in this case, you're kind of too far for it to be like the most damaging. I mean, when you're too close to the epicenter anyways, you won't have time to alert. So this is good for like broader areas. So let's say like an earthquake happens 50 or 60 kilometers away from San Francisco, then you'll be able to give a few seconds of warning to the people who live in San Francisco. But for the people who live right next to the epicenter, then like it will already have happened. So, but that's the best we can do, and that's the best we can do with early warning. I'm not really a specialist of early warning, but that's my current understanding of it.
Yeah, that's helpful.
Okay. All right. Thank you.